Okay. I know in the end of the last video, I said this is the first of 3 videos, but nah, this is gonna be the first of 2 videos. I'm fitting the rest of this nonsense into this one video. A statistical test uses data obtained from a sample to make a decision whether the null hypothesis should be rejected. So I'm letting you know when we are doing research, we are testing against our claim. We test against our claim to reduce our bias. Therefore, instead of us testing our confidence, we are looking for how much error comes from our results. The numerical value obtained from a statistical test is called the test value or the test statistic. The level of significance is the maximum probability of committing a type 1 error. This probability is symbolized by alpha. This A means alpha. The probability of type 1 error is alpha. So when we're doing research, we are testing how much error we have from our results. We're trying to see the probability of us committing a type 1 error. So once again, in research, we are not testing in favor of our results. We're not trying to see how much confidence we have in our results. But yes, we're testing against our claim and we're trying to see how much error comes from the data we have collected. And we do this to try to reduce our bias in our research. Now, here are 2 more definitions I want you guys to write down. And what I'm going to do is I'm going to modify the non-critical region definition because this is more of a research methods definition, but I want to stick to basic statistics. Okay. When we're making a decision about whether the claim that we are testing has evidence in favor or evidence not in favor, we must determine where the test value will fall at. So we have what is called a critical region and a non-critical region. The critical region or the rejection region is the range of test values that indicates that there is a significant difference and the null should be rejected. Remember, the null hypothesis is not what we are claiming. So if our test value lands in the critical region, then we can state that there is enough evidence to support our claim. However, if the test value that comes from us computing our statistical test falls into the non-critical region or the non-rejection region, that indicates that there is no difference and the null hypothesis should not be rejected. So, the non-critical region is the range of test values that indicate that there is no difference, in reality, no significant difference, and that the null hypothesis should not be rejected. So if our test value falls within the non-critical region, we are stating that there is not enough evidence to support our claim. If we do not reject the null hypothesis, then that means we are accepting the null hypothesis. And the null hypothesis is not our claim. The critical value separates the critical region from the non-critical region. The symbol for the critical value is known as capital C period, capital V period, which is right here. Let's keep it right there. Now, we have what is called a one-tail test. A one-tail test indicates that the null hypothesis should be rejected when the test value is in the critical region on one side of the mean. A one-tail test is either a right-tail test or a left-tail test, depending on the direction of the inequality of the alternative hypothesis. Now, I'm going to show you what it looks like when you have a one-tail test, whether if it's a right-tail test or a left-tail test. Okay, so I'm going to show you now a right-tail test. Let's put right over here. Now, I'm going to place a line right here, and this line is known as the critical value, CV. And if you notice, it is on the right. So the critical value on the right side is going to be positive. I'll put a little plus sign for a positive. Keep that in mind. Now I'm going to shade into the tail. And this is a right tail test. Now, the shaded region right here, we call this area the critical region. Let's go up here, critical region. And the non-shaded area is the non-critical region. Now, if your test value lands in the critical region, you reject the null hypothesis. So here you're going to reject the null hypothesis. If the test value does not land within the critical region, do not reject the null hypothesis. Remember, null hypothesis is H0. And finally, the probability of this shaded part right here is alpha. The area is alpha. Now, if this is a left tail test, it will look similar to the one for right tail, except for the critical region will be on the left side of the normal distribution curve. And because it is a left tail test, the critical value is negative. So I'm going to put a negative sign there for negative. And we're going to shade into the tail region. I'll keep doing that. I don't know why. Once again, the shaded area, put a little line in between. The shaded area is known as the critical region. And the non-shaded area is the non-critical region. Now, if your test value lands in the critical region, you're going to reject the null hypothesis. But if the test value lands in the non-critical region, do not reject the null hypothesis. And there you go. That is a left tail test. And the one over here is a right tail test. I drew the right tail on the left side of the screen and the left tail on the right side of the screen. Oh, the irony. Okay. And then we have what is called the two-tail test. Let's zoom out a little bit. Now, for the two-tail test, you have a tail on each side. A tail on the left side and a tail on the right side. So that means you have two critical values. One is negative and the other critical value is positive. It'll be the same number with different signs. Now, we already established before, the shaded area is going to be the critical region. So there's a critical region on both sides. Critical region on the right. The critical region on the left. So if the test value lands in either one of the critical regions, we're going to reject the null hypothesis. However, if it lands in the non-critical region, which is the middle, we do not reject the null hypothesis. And I mean your test value. So do not reject the null hypothesis. And because there are two critical regions, the shaded area right here will be your alpha divided by 2. And this will look similar to when we was doing confidence intervals. Where see, this region right here was the alpha divided by 2, but the middle is your confidence. Okay. So that is how you would draw the bell-shaped curve when you're making a decision to either reject or not to reject your null hypothesis. Okay. Now, just like we had 2 types of confidence intervals, we have 2 types of tests, a z-test and a t-test. We have to find the critical values for a z-test and a t-test. So we're first going to reference, first we're going to find out how do we find the critical values for the z-test, and then we're going to go over how to find the critical values for the t-test. Now, these are the directions that are in your work booklet. However, I am not going to use these directions because I've given you a better piece of information to help you find your critical values for Z. Now we're going to go on to part number 2. And number 2 wants us to find the critical values for a Z-test. And it says, A, using the Z table, find the critical value or values for an alpha 0.03 right tail test. Okay. So it says right tail alpha 0.03. So let's put the right tail right here. And alpha is 0.03. So right here, this is 0.03. And we want to find the critical value. And because we know that it is a right tail test, the critical value is positive. Once again, stated up here, critical value is positive if it's a right tail test. Now, if you go about it the old-fashioned way, remember, we are using the Z table, and every probability on the Z-score table is the area that is shaded to the left. As you see here, the area is to the left of the Z-score. As you can see right here as well, on the positive Z-scores, the area is to the left of the Z-score. However, in this case, the area is shaded to the right. So the first step is we must subtract the 0.03 from 1. So 1 minus 0.03. And 1 minus 0.03 is 0.97. After we do that, step number 2. Go onto the Z table and find the closest probability to 0.9700. And so we're going to do that. We're going to go on the table and find the closest probability to 0.9700. And we will find that right here. 0.9699 is the closest probability to 0.9700. And from there, we're going to find that Z-score. So that is 1.8 8. The z-score is 1.88. And that is going to be the critical value. So our critical value is 1.88. Now, the easier way to do it is to go into the z-score file, the Word document that is right here. Let's clear all this out the way. This is a right tail test. So you see right tail critical value, and the alpha is 0.03, which is right here. Right tail 0.03. The critical value will be 1.88. Which is the answer that we got right here. So that's your answer. So for now on, when it comes to a Z critical value, you can use the z-score file, the z-score percentage document, to find the critical value. For example, using the z-table, find a critical value or values for an alpha 0.05 left tail test. If it is a left tail test, we know the critical value is going to be negative. So let's go on to our z-score file. Now this is a left tail test, so let's clear this. It is left tail 0.05. So the critical value is going to be negative 1.65. So the answer to this question is negative 1.65. And then the last one says, using a z-table, or we can use that z-score file, find a critical value or values for an alpha equals 0.07 two-tail test. Because it is a two-tail test, the critical value is going to be both positive and negative. So go back to the z-score file. This is a two-tailed critical value, 0.07. And the answer is positive and negative 1.81. Plus or minus 1.81. Or you can say the critical value in an alternative way is negative 1.81, comma, positive 1.81. Either answer should suffice. So that is how you find the critical values for a z-test. And once again, you can use the old-fashioned way, and you can read the directions that are up here to find the critical value by hand. Now we're going to do the same thing, but now it's a t-test. We're finding t critical values using the t-distribution. Find a t critical value for an alpha equals 0.05 with n equals 16 for a right tail test. A right tail test, a right tail t-test is a one tail test to the right. And when it comes to a t-test or a t-interval, you must find your degrees of freedom. And remember, the degrees of freedom is the sample size minus 1. I have 16 for my sample size. So my degrees of freedom is 16 minus 1, and that equals to 15. Now, I can go on my t-distribution, degrees of freedom 15, a one-tailed test to the right, and the alpha level is 0.05 to find the critical values. And because it's a right-tailed test, we know the critical value is positive. So t-distribution. Now, if you look here, this is a one-tailed test. One-tail alpha 0.05. Degrees of freedom is 15. Therefore, our critical value is 1.753. So that's positive 1.753. Letter B. You want to find the critical t values for an alpha equals 0.01. Our sample size is 24 for a left-tailed t-test. Because it's a left-tailed t-test, that is a one tail to the left. Degrees of freedom is the sample size minus 1. So that's going to be 24 minus 1, which equals 23. Let's find our critical value. But remember, this is a left-tailed test. So it's one tail. I'm going to keep it in blue, but one-tailed. The alpha level is 0.01. My degrees of freedom is 23. And as you can look here, we have the number 2.500. Now, if you put that as your answer, you will be marked incorrect because, once again, this is a left tail test and critical values for the left tail test are negative. So the answer is going to be negative 2.500. Just make the sign of the critical value negative. And last, but certainly not least, find the critical values for an alpha equals 0.10 with the sample size 18 for a two-tailed t-test. Let's find our degrees of freedom, which is the sample size minus 1. So that's going to be 17. And now let's find the critical values. Because it's a two-tailed test, it must be negative and positive. So now I'm going to do it in red. This is a two-tailed alpha. Critical value 0.10. Move this out the way. And my degrees of freedom is going to be 17. Let me double check to make sure that's correct. Degrees of freedom is 17. So that is going to be 1.740. But the critical values will be both negative and positive. So it's going to be negative 1.740, positive 1.740. And if you want to, you could have put positive negative 1.740. Same thing. Okay, guys, that is it on how to find your critical values. So I think we are ready to actually run some hypothesis testing questions. Yep, we're definitely ready. And I'll be in the next video. Take care.